This is liquids and intermolecular forces, and the first part of this chapter is going to be the intermolecular forces. These are actually longer sections than they will be in the next chapters. Gases, remember, are widely separated, disordered particles. Remember, we did gases in chapter 10 last semester, or if you were somewhere else, whichever chapter, there was a single chapter. And so we know that there's most species are liquids and solids, but gases are special, widely spaced, or separated, disordered particles in constant motion. Liquids, on the other hand, are closely spaced, and they still move, but they have limited motion, because remember, a gas will take the shape of the container, whereas a liquid will only occupy the bottom part. They are still disordered, like gases, but instead of in all over the container, they're just at the bottom of the container. And solids, on the other hand, are closely spaced, and that's similar to liquids, but instead of being disordered, they're in ordered positions. And the positions are fixed. Now, that's not to say that there isn't motion. It's like a vibration in place. So, for example, if we were to turn off gravity, if you were in a classroom and you were free floating, then you'd be a gas. If we put you at tables where we had benches so you could slide up and down the benches, you would have more order, so you'd be a liquid. If we replace the benches with seats and you had to sit down, again, when you sit down, you're still taking notes and you're still wiggling in place, but you're still in place, so then you'd be a solid. And remember, we can move between these states using temperature or pressure changes. Okay, now why does this have an effect? We'll look at why it has an effect and why some species, like chlorine, is a gas. Bromine, however, in the same family, is a liquid, and iodine is a crystalline solid. So they're all in the same family, so you'd think they'd be similar to each other, but they differ by their state. Okay, this is just a table that combines all that we've just gone over. Now, what is going on? Well, we have three things. The first one is a bond, and this is a bond, and they're going to form between different atoms. To form molecules. And so we did covalent bonding at the end of 1211. So we talked about sharing electrons. These are bonds. These are very strong. And they hold atoms together. Now, this is very different than intermolecular forces. I call this IMF, intermolecular forces. These are the interactions between these particles. And they can be a variety between different molecules, salts. So remember, a salt is a four-letter word for non compound, ions, etc. So they can be between any variety of things. So if you think about it, you're gluing two things together is a bond. If they're magnetic and they stick together, but you can pull them apart, they're more of intermolecular forces. Now, in intramolecular forces, and inter means between, intra is within. This involves the interactions within the same molecule. Now, if you have a small molecule like water, you're going to have bonds. You're not going to have intramolecular forces. Okay, this is, if you, as you go on to biology, these are the proteins. These are the ions and molecules binding in sites, etc. And I like to use proteins because if you're talking about alpha helixes or beta sheets, when you talk about protein folding, you're talking about intramolecular forces. You're using the intermolecular forces, but instead of between two molecules, you're using them within the same molecule, and that's why you get the particular shapes that you get. And so I always find it fun once you get into the biology to look at some of the 12-12 stuff. Now, intermolecular forces will define a lot of properties of a molecule. So when we talked about properties of atoms, we talked about protons, neutrons, and electrons. But here we're looking at the molecular compound, and so we want to be able to compare them. Okay, now what do they affect? Intermolecular forces, and remember, I'm going to call them intermolecular forces, IMF, will have an effect on the physical state, whether something is a solid, a liquid, or gas, etc. It'll have an effect on the melting point and the boiling point of any variety of compounds. And basically, as the intermolecular forces go up, your boiling point will go up, your melting point will go up, and the condensed state goes up. Now, what is the condensed state? Well, as you increase the intermolecular force, you're becoming more condensed, so you're more likely to go to a solid. That's the most condensed. The least condensed state would be the gases, and liquids are in between. So, what types of intermolecular forces are there? Well, there are three types. London forces, LF, also known as dispersion forces or van der Waals forces. Depending upon where somebody was educated, etc., it's kind of like saying y'all in the South, you will get different names for London forces. In some biology, they call van der Waals forces the London and the dipole. We separate them out. So London forces are also known as dispersion forces or van der Waals forces. And we'll go through each of these in detail. Then the next one, it's a little stronger, is the dipole forces. This can involve the dipole and an ion. Again, more about this. And then hydrogen bonding. Now, this is a misnomer, which is a fancy word for saying it's misnamed, because it's not a bond. Okay, and I'll point that out again. It's called hydrogen bonding, but it's not a bond at all. It is an intermolecular force. Okay, so let's go through each of these individually. And the first one is London forces. So we'll start up here with two molecules. Now, the other thing that you need to remember when you're talking about polarity, let me erase that. You're talking about electronegativity. And remember, if you don't remember that, you want to go back and review. But electronegativity is the ability to distort an electron cloud by uneven distribution of electrons. In a bond, you distort it by pulling the electrons towards itself. So in a bond, electronegativity allows the electrons to be pulled towards more atoms. If they pull too much, then you pull it totally over, you become an ion. If you gain it, you're negative. If you lose it, you're positive. So if you remember back, if you self-bond species that are electronegative, and let me go ahead and list them. Fluorine is your most. Oxygen, nitrogen, and chlorine are next in this order. Then you have halides and sulfur, and then it drops off from there. So basically, electronegativity increases as you go up to the corner. Just think of fluorine is the biggest bully on the block. Remember, under oxidation rules, it was the only one that was always negative. Oxygen was mostly negative except in combination with fluorine. So oxygen is going to be negative except when the biggest bully is in the block, which is fluorine. Okay, so back to the chlorine. This is a non-polar bond because the electrons are evenly shared because the difference in electronegativity between two chlorines is 0. So what happens is if you think about the electrons going around in circles like laps, okay, then at some point in time you end up with less electrons on one side and more electrons on the other side. More electrons. Okay, which then causes this to become a partial positive and this to become a partial negative, because remember, a negative is going to repel the electrons. And so we end up with this arrangement. So we have a partial positive attracted to a partial, again, if I could, there are two T's in attract. Okay, fine. Again, spelling is optional, guys. Attraction. So then you'll have the attraction. Now here's the beauty or ugliness about this is it's instantaneous. That means it's in fractions of a second. It forms and then disappears. Second, it will form and then disappear. All right, if you have ever been to a game, I know before the COVID virus, remember back when you went to go to a stadium, football, baseball, whatever, and they did the wave. So what happens is everybody's sitting down and then some people stand up and then, you know, you stand up as you show up and then then you sit back down and the standing keeps going. So a good wave that's done around a stadium, and if you've never seen one of these, you can Google it. But a good wave going around a stadium is very much what London forces look like, except infinitesimally faster. Okay? The wave in a stadium is very slow and low. Okay, so basically you have this uneven distribution and then it relevels out, uneven levels out, and it causes interaction as it goes. All right, so here's a figure out of your text. If you'll notice, they're doing this on a subatomic level, and here you have your uneven distribution of electrons. And when you do that, then it automatically causes an uneven distribution here. As this one goes back and moves it on down the row. So you have this interaction. It's called an induced dipole or dispersion force as it goes along. And again, with the London forces, it forms instantaneously and then goes away. So if you look here, we've got neon and fluorine. They're in the same row. Argon and chlorine, chromium and bromine, xenon and iodine. So the question becomes, why is there such a huge discrepancy? Because of polarizability, which is the ability to distort an electron cloud. So if you can distort the electron cloud more easily, then you induce a dipole. Clowns. Ha! There are no clowns in here. Okay, maybe me. Clouds and distort. And induce a dipole. So let me, now that I've got this one written down, let me look at it. Okay, polarizability is the ability to distort the electron clouds and induce a dipole. So if you look at it, the main difference between neon and fluorine is, if you look, all of these are diatomics. And so one of the factors that goes into this, and we're going to see this in a minute, is size has a bigger difference. So as the polarizability increases, you increase the intermolecular forces. So polarizability is the main issue for London forces or London dispersion forces or induced dipoles. So what are these factors? Well, the first thing, as I mentioned before, and you can see it on the previous side, as you increase the molecular size, you increase the polarizability. And the polarizability, if you're inducing an electron cloud to distort, I call that squashiness if you're thinking about it. Think about a golf ball. Excuse me, yeah, a golf ball or a ping pong ball. Something, a small ball. And it's made of a particular material. It's flexible, but not real flexible. So when you try to squeeze it, you really kind of can't. So let's take that same material and make something the size of a bowling ball, about 8 inches across. Now, same material, it's easier to, squish it in or poke it or whatever. Even though the material may be a little rigid, it's not hard like an egg. It's got a little flex to it, but you can flex it, but a lot more than you could the golf ball. But still, it's not huge. Well, let's take that same material and let's make one of those like 6-foot beach balls, 5-foot beach balls. I've never actually played with one that people play with on the beach or at stadiums or whatever, where they put people on them and they roll around and they bounce on them and that type of thing. If you'll notice, the same material, that becomes way more squashy. So if you think about it, as the size increases, it's easier to distort the shell in this case. So if you got a molecule and you got the electrons going around, if you only have a small space with a few electrons, then it doesn't distort much. Okay, you can think of this as herding puppies. Okay, you put them in a really small pen and you got 4 puppies, no problem. Put a bigger pen, more puppies, you're much harder to herd. You put them in an entire yard, you're chasing those puppies for days. Okay, so as size increases, polarizability increases. All right, now the number of electrons. As you increase the number of electrons, you increase polarizability. And this makes perfect sense because we're back to the puppies. If we have 4 puppies and we're trying to catch 4 puppies, then, okay, that's still hard. But let's go with 1 puppy. You can catch 1 puppy. You put in 2 puppies, you can catch 2 puppies, but it's a little harder. Let's put 3 or 4 or 5 or 6 puppies in. And even unless you have a teeny tiny spot, catching puppies is hard. Same thing here. Oh, one other thing I want to state is up here with the size. Some people use the molecular weight, not size. This works most of the time as long as you're not looking at part C, the third one, which is branching and stuff. But this is not a good idea. You really want to go with the size, not the molecular weight, even if you're talking about atoms, because in the transition metals, you have a size differential, whereas the weight kind of can bounce back and forth because you can actually go down in weight and up in size and vice versa. So far we got molecular size and number of electrons, and then molecular shape. Now this is where things get a little wild, because this is where this becomes a huge issue when you go on to organic, is looking at with respect to the molecular shape. The molecular shape really defines surface area. Okay? So as you increase surface area, you're going to increase polarizability. We're back to increasing the size, you're increasing the polarizability. Okay? So we're going to look at a slide in just a second, but let's look at an actual situation. And these are all in the same family. These are all the halogens. And if you go down the periodic table, we don't even put fluorine on there, but it's a gas too, and it's never not a gas. And the molecular weight around it is about 40. But they look at these because this is where the change occurs. This is a gas, this is a liquid, and this is a solid. So if you'll notice, as you go down, you're going to increase in size. So as you increase in size, you get more intermolecular forces, and your melting point and your boiling point go up. So you can see this within a family. All right, and the other thing to remember is all molecules, not ionic compounds, but all molecules. And remember, it's intermolecular forces. All molecules will have London forces. They may not have anything else, but they'll have London forces. So we're back to the molecular shape affecting the polarizability. And here we've got them all with the same formula. Now the trick to this is they may all have the same formula, but they don't have the same boiling points because they have different branching. So this is where mass will not work. Size is definitely a factor. And if you think about it as just attaching the 5 carbons, this is a long chain. And the easiest way to think about this is take a tray, any sort of tray, and put water in it. And the tray needs to be, long and flat. So as you walk with it, it's really hard to keep the water from sloshing around, right? Because it has the most surface area and it wants to keep moving. If you branch, and again, if we just put the carbons here, we take 4 carbons and we branch one off there, so that now it's a little more compact. So instead of having a tray that's flat and narrow, we've got a box. You're still going to slosh. But over here, we take the same 5 carbons and we put it basically into a ball. So put the same amount of water in a pitcher or a bottle of some sort and carry it. Well, you don't tend to spill as much because it has much less surface area. So as you increase branching, you decrease surface area. And then remember, as you decrease surface area, you decrease the intermolecular forces. Okay? So as you get larger, you have more polarizability, more intermolecular forces. As you decrease the surface area, you have less surface area and less intermolecular forces. So the bottom line on this is these are the same molecules. The mass doesn't change. But the structure changes, so it has a huge effect on the polarizability, which is why I'd be careful using mass. It'll work if you have a broad thing, but if you're within the same mass, you have to look at the shape. Okay, so then that comes to the question of which of the following molecules will be more polarizable. Well, you're given a periodic table, so if you look at the periodic table, you'll notice that these are all in the same family. Well, that was easy. Okay, so as you go down the periodic table, your size is going to increase. As the size increases, you increase polarizability. So in this case, tellurium is the largest, so it will be the most polarizable. So if I had asked that polarize, okay, we're just leaving it there because I can't spell it. If I said what would be more, you would go with that one. Now, if I had said least, then you would go with oxygen here. Okay, so watch out when you're asked questions like this on a quiz or an exam. For us, we're calling them exams, but they're done in quiz format in D2L. Then you want to know most or least because it changes the answer. Okay. So here we go. Arrange following molecules in order of increasing polarizability. So first things first. 1, 2, 3, 4, 5. I have 5 carbons, and there are no branching. This one I have 3 carbons. This one I have 1, 2, 3, 4 because it has a 2 here. 5. So this one's going to be 4 carbons in a row with 1 branch. So it's 5 carbons. 2, 3, 4, 5. Oh wait, it has 2 carbons off of it, sorry. And this one's straight chain with 1 carbon off. So this is still 5 carbons. So first things first, we're going to arrange it in order of decreasing polarizability. So we're going to have most polarizable to the least. Okay, so if we're looking at this, polarizability increases with increasing size. So which one's the smallest? This one's easy. At least that end is the 3 carbon. So if we're looking at it, the most polarizable, if we look at the other ones all have 5. But the 5 carbon, and they all have 5 carbons. So I'm going to call this one A, this one B, and this one C. Okay, I could rewrite the structure, but that gets a little wild. So the most polarizable is going to be the 5 carbon that's a straight chain. We call those chains in organic. So that would be A. All right. So then we have, as you increase branching, remember you decrease surface area. So if no branching has the most surface area, then 1 branch, so that would be 5 carbons, 1 branch. It's 1 branch. This one's 2 branches. So this one, as I've got them labeled, would be C. And then 5 carbons, 2 branches would be B. So most polarizable would be A, then C, then B, then D. So just greater symbols would go there. All right, so you might have problems like this on the exam, quiz, whatever. They'll most likely be in multiple choice format. But in this particular case, if you could do a little work and submit that just in case you're wrong, you might be able to get some partial credit because this might not be just a 1 or 2 point problem. I'm going to say this several times when I talk about the exam, but I want you to keep in mind that work is relative and partial credit hinges upon you turning in clear, readable work. Okay? So the next intermolecular forces is dipole. And we're back to, you have to go back and review 12, 11. You must have a polar molecule. Okay? Now that means it has to have a dipole moment. Okay, what is a dipole moment? It has the symbol mu. That's a mu. Okay, a dipole moment is where you have a polar molecule with an unsymmetrical shape. So you end up having a net, partial positive, partial negative region in the molecule. And we remember the partials are given by this. And remember, these are not full charges. Not full charges. Full charges are known as ions. These are dipoles. And what we have here is, just like magnets, the negative is attracted to the partial positive. So this keeps hanging together, and since these stay as partials all the time, unlike London forces where they form and go away, these stay all the time. The interaction is much more steady and more stable. So dipole forces are way stronger than our London forces. Okay, this is my weirdo drawing that I did. These are dipole forces. Whereas over here, you're like, wait, we got a cation ion. So this is dipole ion forces. So dipole forces include dipole-dipole and dipole-dipole. ion interaction. Okay, that having been said, then what we see here is, if you'll notice, and as I said, I did these should all be partials, but I was having a hard time with it. So if you'll notice, the negatives are attracted to the positives, and the positives are attracted to the negative. So this is why, and we'll get into this again later, but this is why polar solutions will dissolve salts and nonpolar will not. Okay, here's another figure. This one's out of your text, and this shows you that not only do you have attractive interactions between the partial positives and the partial negatives, you will have some repulsion between the two partial negatives. So the molecule is kind of like playing with the little magnets where you put them together and they start flipping and stuff until they're happy in their alignment. They still have a little repulsion going on, but it's minimal. And here we have three polar molecules. This one is nonpolar. And if you'll notice, these are the dipole moments. The larger they get, the more polar. So what you'll notice is as you increase polarity, you're going to increase the dipole interactions. Okay, which actually makes perfect sense if you look at it. And remember, these are the space-filling molecules. You'll tend not to have those on the test because they're kind of hard for me to draw in. Okay, so the next one is hydrogen bonding. Okay, remember we stated this before. It is not a true bond. It's only about 15% of the strength of a bond. And there are three things associated with hydrogen bonding. First off, you must contain a hydrogen attached to an electronegative species. You must be a polar molecule. And you must have an electronegative species with lone electron pairs. Your most common ones, remember, are fluorine, oxygen, nitrogen, chlorine, halide, sulfur, and it drops off from there. So you're going to see this. And you'll still see it with this. Now, you're like, chlorine is the same as nitrogen. Yes, it is. However, nitrogen is in every protein you've got. Chlorine is not. So that's why nitrogen is listed and chlorine is not. And these are the strongest of the intermolecular forces. And the most common place to find them is water. So here we have our hydrogen bonding, because remember we have a permanent dipole. Remember we have two lone pairs over here on the oxygen. So what happens is the lone pairs interact with the hydrogens, which are the partial positives, and that's why they interact as they go. And so hydrogen bonding is the strongest, and water is your set point basically for it, in terms of, if it wasn't for the hydrogen bonding and the interactions in all the water molecules, you'd be a puddle because you're mostly water. All right, so in this slide we're looking at the different groups, and group 7A are the fluorine halides. This will be the oxygen group, the nitrogen group, and the carbon group, basically. And so the families are groups. So what you'll notice is that there's a huge increase here because of the difference of electronegativity and the ability to hydrogen bond. And then from here we drop off because there's no hydrogen bonding. Okay, now as it increases in size, you increase the London forces. But small molecules with no intermolecular forces don't have much. All right, now this is one of my favorite slides because it puts it all together. Okay, dispersion forces, or London forces, as I like to call them, are the most common. And if you'll notice, everything has them. Okay? And be careful over here because this is ionic solids dissolved in polar liquids. This is just not ionic salts. And over here, hydrogen bonding are the least common. They're the strongest. And strongest, if I could spell. And I call the ion dipole a specialty because the ions are not molecular species. They are ionic species. But they do interact when you get into polar molecules. So let's work a problem here. What intermolecular forces exist in the following species, which is most likely to exist in the gaseous state? Well, bottom line is gases have the least intermolecular forces. So let's look at them. I'm going to separate them out. So P4H10. No. Well, it'd be nice if I could write it right, correct? So O10. So what we have here is we have a lot of P's and a lot of O's. It is a molecule, so we know we're going to have London forces, and I recommend you start at London forces and work up. Give you a hint, you can't have hydrogen bonding unless you have dipole. So try not to work it the other way. So we have phosphorus and oxygen bonds. Not really sure what the structure is, but you got four phosphoruses. They're going to be attached to some oxygens. Not really sure what this structure looks like, but odds are it's not going to be perfectly symmetrical. So we're going to probably have a dipole. Okay? Chlorine is a halogen. It's a diatomic. It has a polarity of 0 because, yes, it's an electronegative species, but it's self-bonded. So the only thing it's going to have is London forces, no dipole. Silver chloride, on the other hand, silver is a metal, chloride is a nonmetal. So wait, this is a salt. And remember, salts don't have intermolecular forces. Hi is molecules, so it's got London forces. Iodide is in the halogen family, so it's going to have a difference in electronegativity. So we'll have a dipole. It has a hydrogen attached to an electronegative species with lone pairs. So it has, whoops, hydrogen bonding. No, we already did lone forces. Okay. It's probably time for me to stop doing these if I'm going to make these fun, stupid things. All right. So the question then becomes, which is least likely to exist in the gaseous state? So we're looking for the lowest intermolecular forces. So that would be chlorine. And if you're like, well, but salts has none, it's not even intermolecular forces. Salts are held together by strong positive and negative charges, which they're crystalline most commonly. Now, if, for example, I looked at this, eliminating the solid, which one has the most intermolecular forces? That'd be HI. And we'll look at some of these problems as we go. Okay? So, here's another set of the following species: bromine, neon, hydrofluoric, acetylene, C2H2, and ammonia. Then the questions are, what has the greatest, least, largest intermolecular forces? Okay? All right. So here we go. We're going to line them up. Bromine, neon, HF, C2H2, and NH3. Okay? Should have left more room with the other side, but okay. All right. Bromine is an electronegative species, but is self-bonded. So it's going to have London forces. Because it's self-bonded, the difference in electronegativity is 0, so it's going to be nonpolar. Neon, yeah, it's not a molecule, but it's a single atom, so we can deal with single atoms. It only has London forces. HF is similar to HI, which we just did. It has London forces. It's definitely a polar molecule. So it has a dipole, and remember, the halogens all have 3 lone pairs, so it definitely has a hydrogen attached to an electronegative species, and the electronegative species has unbonded pairs, so it has hydrogen bonding. Okay, C2H2, most of y'all have slept. If you took my lab, you've already seen this one. But that's what acetylene looks like. It's a triple bond between the 2 carbons with the hydrogens attached. So first off, it is molecular, so it's got London forces. Now, if you remember back, if you were in my class, and if you weren't in my class, I'll restate it. All carbon hydrogen bonds are non-polar. So in this case, there's no polarity, so we got nothing more than London forces. Okay? Now, ammonia, I will draw that again, since, again, y'all have slept since last you saw it. You have ammonia. Well, again, it's a molecule, so we definitely have the London forces. If you'll remember, it has polar bonds and it is an unsymmetrical molecule, so it has a dipole. And it has a hydrogen attached to a nitrogen, so it also has hydrogen bonding. Okay, so then that begs the question, which one has the greatest intermolecular forces? So we have HF and we have NH3. So if we said which has large intermolecular forces, both of them would qualify, but we said which one has the greatest. Well, we talked about the fact that of the bonding, hydrogen bonding is the strongest of all your intermolecular forces. So we know that that's the strongest. So the question is, how many do they have? This one has 1 hydrogen bond. Well, look at ammonia. It has 3 hydrogen bonds possible. So which one do you think is going to have the greatest intermolecular forces? I'm betting NH3. Okay. Which has the least intermolecular forces? Well, that brings us to bromine or neon. Now, what's the difference between bromine and neon? Size. As you increase size, you increase London forces. Which one's the smallest one? If you remember your trends, that's the neon is definitely the smallest one. It's smaller than a single bromine, and then you double the bromine, so it's huge. So then the next question says, what is the largest London forces? Oh wait, we just did this. If neon is the smallest, then bromine is the largest. And then the other question is, which one has the smallest dipole forces? Well, if we look at it, the only ones with dipoles are HF or NH3. So if you're looking at it, the dipole has to do with the interaction. Remember, if you're looking at electronegativity, then fluorine is much more electronegative than nitrogen. Now, it'll come into play if we had more data and we could actually look at the values, then you might get a difference in nitrogen because of the size and the vector once you combine everything. But for what we have, we're just going to go with electronegativity. So if fluorine will be the most electronegative, then the least dipole force will be ammonia. Okay? Now, this is not asking for the net overall dipole moment, because that will vary as you put in the spatial considerations, etc. So, again, you may have a problem like this on the test, you may not, but the bottom line is that you need to, if you present work, this is plenty of work. And notice, it's not a whole lot of writing. It is strictly laying out the information that you've got. Okay? So then we go back on to the last problem here, which is the intermolecular forces associated with the boiling point. All right, so as you increase intermolecular forces, you're going to increase boiling point. Okay, so if we look at this, CH and CH4, which is methane, and we said that carbon-hydrogen bonds are nonpolar. So the only thing we've got here is carbon-hydrogen. So it's London forces. The other one is London forces as well, because silicon's not very electronegative. Carbon and silicon are in the same family. So if you're looking at them and you look at a periodic table, you have carbon on top and silicon there. So this is much bigger size-wise. So as we increase size, we will increase the London forces. So the higher boiling point will be silicon tetrafluoride. Okay? All right, so that's how we explain briefly. Here, this is a salt. It's ionic, whichever one floats your boat. Same thing. This is chloroform, and it has this formula right here. So we know it's molecular, so it has London forces. And you look at it, and so we got carbon and chlorine bonds on 3 out of the 4 sides. It's a tetrahedral, so it's got polar bonds and it's unsymmetrical, so it will have a dipole. Will it have hydrogen bonding? No. We have the hydrogen, but it's attached to carbon, not an electronegative species. So we don't have hydrogen bonding. So again, we're asking for the higher boiling point, so it's which one has the greatest intermolecular forces, and in this case, the salt wins. Because it doesn't have intermolecular forces, but it's a salt. So therefore, it will definitely have the higher boiling point because it's actually held together by positive and negatives. Okay? So for this molecule here, we have CH3, CH2, chlorine, or CH3, CH2, CHOH. Okay? Yeah, I put an extra carbon in that. Let me erase that. Okay. All right. So if you look at it, this is similar to HOH, but we replaced one of the hydrogens here with this group. Okay? So if you're looking at it, this part of the molecule is nonpolar, not much of it, but it is nonpolar in both cases. So the same is said. So it has London forces. Both of them are going to have London forces. All right, this is a polar bond. And this is a polar bond. Actually, as is the OH. So we have polar bonds. So both of these are a dipole. Now the chlorine doesn't have a hydrogen attached to it, so it can't have hydrogen bonding. But the oxygen has a hydrogen attached to it, so it has hydrogen bonding. So the one with the most intermolecular forces, which is C2H5, also known as ethanol, will have the higher boiling point. Now remember, I could have asked for the lowest boiling point, in which case you would have the same work, but all of your answers would be opposite. So when you look at these problems, first thing you need to do is identify the intermolecular forces associated with them. And the second thing you need to do with them is look at whether I'm looking for a high or a low boiling point, melting point, whatever. Okay? So these aren't really that bad. It's just a matter of looking at the properties. And again, please go back if you don't remember the structures and review in chapters 8 and 9 to look over the molecular shapes and polar molecules, and that will help you tremendously. Okay, last slide is one of those little lanyard thing, and this has to do with ionic liquids. And this is actually a very important property because what you're doing is you're forming a, here especially, this is an organic molecule which is not soluble in water, but you're protonating it so that it becomes a salt. This is exactly what they do with a lot of medicines. They'll have a carboxylic acid group or amine group or any variety of polar groups that they can slap a hydrogen on. If you'll notice, if you read your medicine labels, and I highly recommend that, and if you don't have any because you're in perfect health, go borrow your grandparents, your parents, your friends, and just read the labels. Don't take the drugs. You read the labels and see, but a lot of medicines will have whatever the drug is and then HCl. It's not that they're adding HCl on just randomly to the solution. What they're doing is they're adding the hydrogen to make it a cation to the drug, and then they counter it with the chlorine. And the beauty of this is when it hits your stomach, it will dissolve. Otherwise, it wouldn't dissolve. So it's a way to get medicines in. So this little lanyard is very interesting and useful to understand how things work.